I should say that that award was for my administrative skills, I think. All right. So what we're talking, or what we're celebrating in this series of talk, is this curtain here. I've actually never seen the curtain, but if you look closer at this curtain, you will find Bayes' theorem somewhere there. I've written out the equation, and during this talk, I will talk about the equation. I will tell you how it came about, and I will spend quite some time talking about how people really found it hard to accept this rule or theorem. Digital futures is a quite broad area or project, so I won't go into nitty-gritty, super gory details. I will try to stay at a level that is understandable for everyone, hopefully. And as Erwin said, I got really caught up in reading this book about history, and maybe my talk is maybe too much influenced by that. We'll see. So the agenda is I will give a brief recap of probability just to make everyone be on the same page. I will look at an example to put this into context, and then I will go into the history. And then at the end, I will use Bayes' theorem in some more examples. All right, so let's start with the basics. Let's say we have some event A. So we define P of A to be the probability of that event A. And this event might be that it rains tomorrow, or that I break my leg, or whatever. We then talk about joint probabilities between two events, A and B. And this could be that it rains tomorrow and the day after. We talk about conditional probability. So the probability that some event A happens given that C has happened. And if we go back to the weather example, it would be maybe that, let's say that it's raining today, which would be event C here. Then using that information, what can we say about the weather tomorrow? Will it rain or not? If you have variables like A and B that can be true or false, it's quite common to, by A, say that A is true, and then this not symbol to say that it's false or didn't happen or fail, depending on the context. Probabilities are between 0 and 1. One of the basic rules that we tend to come back to often is the sum rule that allows us to do marginalization over joint distribution across other variables, denoted by BI here. We also have the product rule that links the joint distribution with the conditional distribution or probabilities. And this allows, if you combine these two and put the product rule inside the sum rule, we get an equation that allows us to express the probability of some event A in terms of conditional probabilities over some variable BI. So we're basically enumerating all possible outcomes of this B and calculating the sum. All right, so far this is standard stuff you've done in some classes probably, and you've probably also done the next thing, which is to derive Bayes' rule. So if you start from the product rule, then there's nothing really special about A and B here, so we can switch the place of those. So we can say that the joint probability AB is the same as the joint probability over B and A. If we use that, then we can put the left-hand side of this top equation here by switching A and B, and we get the expression at the bottom here. And if we just divide by B here, we get Bayes' rule. So this you've done probably. And as Erwin said, this is something that we use a lot today. Like it really, at least in my research, I use it a lot and have used it for a long time. And upon preparing for this presentation, I reflected on the fact that back when I was a PhD student, I sometimes heard that someone's, like they made a big point of that this was Bayesian. And I didn't reflect so much about it. But now I mean, really, this conflict between frequentists and Bayesians really became very, very vivid when I studied this material. And I hope to tell you a bit more about it. So it had a really bumpy ride through history, and we'll get back to that. But first, we'll look at a bit more basic probability. So let's look a bit more at conditional probability. So in my homebrew Euler diagram here, I have two events A and B. So this rectangle here represents the different cases that would allow us to say that A is true, and inside this rectangle B is true. And then the conditional probability is defined by looking at the sort of this intersection where both the joint probability of A and B, so this little area here, the ratio between that and the area of B here. And we can, of course, look at the opposite here. We can look at the joint probability of, or the conditional probability of B given A, and then we would look at a different ratio. So let's look at another example here. So if you have a case here where we have event A and we have events B1, B2, B3, then the unconditional probability of A, we would get that by looking at this region here where A is true, and we would sum the different contributions to that. So we have one piece here where B2 is true, we have one where B1 is true, and then we have the rest here, which is all of the other area here. So together we would just sum those, and we would have the unconditional probability of A. If we want to look at the conditional probabilities for the different BIs here, so if we know that B1 is true, then, well, if we know that B1 is true, we also know for sure that A is true, because in all cases where B1 is true, A is also true. If we instead want to look at the conditional probability of B given A given B2, well, then we're in this area. So we know that B2 has happened. And in this part of B2, A is also true. So we would look at the ratio between this region and the full size of B2. And the same way for B3. So in B3, if we know that B3 has happened, then there is no overlap between A and B3 here. So the conditional probability of A given B3 would have to be 0. All right. So another key concept is probability distribution. So far, we looked at variables that can be only true or false, but in many cases, the variable can take on many values. And then to describe that, we look at the probability distribution. So here we have a case where we have two different variables. So if you first look at this image and concentrate on the blue dots here and see how they are sort of spread out in the horizontal direction, we could describe the distribution of those in a histogram that is shown in the bottom here. If we instead look at the blue points, but think of how they're distributed in the virtual direction, we have so this is what they're called y in this picture here, and then y only have two possible values, so we get a histogram with only two bins. And well, this is the same case like we had before, something that you could think of as being true or false. It could be 1 or 2, but that's more or less the same as being true or false. And because we know that the probability of all possible events, if they are sort of exhaustive, then we know that if we know the value of this one, we can calculate the other one by just taking 1 minus the first one. All right, so we talked about conditional probabilities. And here we see that the case where we know that y1 has happened or is true. And this means that we're really focusing on this part of the distribution. So given that we know that y is 1, we know that these blue dots, or those blue dots represent the type of outcomes you would expect in that case. And we see how the distribution of x shifts from having this information about y. And this will be one of the core insights here in the lecture, or in Bayesian theory in general. So by measuring, in this case, this y, it tells us something about x as well. And then, of course, variables could be continuous. And in that case, we talk about density functions instead. So in this bottom right figure, we have on the x-axis here, we have different values that x might take. And then the red curve shows the density function. So something that says for a certain region here along the x-axis, how likely is it to get a value of x in that region? The same as before, the density function should be larger than or equal to 0. We can look at the probability of getting a value of x in some interval between a and b, for example, by taking the integral. And in many cases, even when we sort of treat the problem as being a discrete one, the underlying problem is continuous, and we can go between those two representations by discretizing our continuous function. So imagine sort of creating small bins along the x-axis. We can go from a continuous function to a discrete one. If we want to express the sum rule, then we would have to exchange the sum for an integral in the continuous case. Another important thing in this case when we talk about densities is the so-called cumulative distribution function, or CDF. This is something that tells us what is the probability to get a value that is less than or equal a certain x. We see that this is a monotonically increasing function. All right, so let's look at an example. I should say also that in most real world cases, the variables would be multidimensional as well. So it might be a 100-dimensional space that we're trying to estimate or predict something. But let's look at an example. So this is an example about breast cancer. And its starting point was that there was a task force in the US to look at whether or not one should do mammograms sort of in a mandatory fashion. This is something that is typically done for women in their 40s. And they suggested that maybe we shouldn't do this. And the public was quite angry. So let's look at trying to figure out why this task force might have said that we shouldn't do this. And let's do that by starting by looking at the probability that the woman with a positive mammogram has cancer. And to do this, we can use Bayes' rule, which if we sort of replace our A and B from before with having cancer and getting a positive response from the mammogram, would give us an equation where we can then, on the left-hand side, we have the thing we want to calculate. So given that there is a positive response from the mammogram, what is the probability that we have cancer? And Bayes' rule allows us to express that instead in terms of the so-called likelihood. And you'll notice that this is, like we said before, this is flipping the A's and B's. And in this case, we're looking then at the probability of getting a positive mammogram, given that we have cancer. Then we have the so-called prior here, the probability of having cancer, sort of the unconditional probability. And then we have the probability of having a positive mammogram, again, unconditionally. In order to make some calculations here, we need some data. And the source 2 here that I will reference soon presents that type of data. They said that there's a rough chance of getting cancer at about 0.4%. So in 10,000 women, there would be about 40 that have cancer. And then if you look at the sort of the performance of the mammogram as a technology, then they will identify about 80% of those that have a cancer. So those would be the true positives. And about 10% of the cases where the mammogram says this woman probably has cancer, it's actually false positive. And now, in order to use Bayes' rules, we have to calculate these quantities. So let's do the math here. So the first one is easy. It said that 0.4% have cancer. That gives us the unconditional probability to be 0.004. The next one is also quite simple. If you want to calculate the conditional probability of getting a positive mammogram given that you have cancer, then, well, that's that's the performance of our detector. So that was 80%. If we want to calculate the prior for the unconditional probability of having a positive mammogram, we have to do a bit more work. So let's consider a population that did the mammogram. So all of the people we look at now have done a mammogram. Some of those will have cancer and some will not have cancer. So we know that 0.4% have cancer and 80% of those will get a positive mammogram. So that would contribute 80% of 0.4%, so 0.32%. We also know that since there is 0.4% that have cancer, we know that it's 99.6%, so 100% minus 0.04% that don't have cancer. And we know that those that didn't have cancer, it was about 10% that resulted in a false mammogram. So that gives us 9.96% that got a false or got a positive mammogram result. So those two contributions are the ones that give us the prior for a positive mammogram, which then turns out to be about 10%. And we can plug those numbers into base formula, and outcomes that it's about 3% chance that someone with a mammogram that is positive actually has cancer. And I think for most people that are not used to this type of reasoning would say that, whoa, that's a really low number, only 3%. Our detector was 80% reliable. So why is it so low? But we have to remember that it's quite low probability that we have cancer. And this is what influences this. So let's look a bit closer. Why did the task force advise against large-scale screening? Well, there were 32% in a population of 10,000 people. There were 32% that would actually have cancer. But for those 32 people, we would send out letters to 996 other people and say that your mammogram was positive. And that would probably lead to quite a lot of anxiety, and we would have to screen a lot of people, and it would cost a lot of money. So it costs a lot, and we create a lot of anxiety. So that was the reason why they said that maybe this is not a great idea. And we have similar discussions in Sweden as well. All right, so let's analyze this. What are the pros and cons with using a Bayesian approach here? So the pro would be that we could factor the problem into pieces. So if we want to calculate the probability of having cancer given the mammogram, we can factor that into 3 pieces that are probably easier to calculate. It requires less cross-referencing across different registers, maybe. We could also imagine that we could account for per person background disease history. So you could further sort of refine this unconditional probability of having cancer by taking in maybe BMIs or other diseases that might influence the chance of having cancer. And we can combine our prior information with data in a nice way. The downside, well, we have to use priors in some way. And this is, as you will see in my history description here, this has caused a long debate, and many consider it to be sort of ugly because we're doing this a bit to calculate those priors in many cases. And you could also imagine that if we adjust the prior, the result would we would get a different result. And that also doesn't go down well with many people when you try to convince them of the validity of your result. Another thing is that if you have very complicated cases, then the cost can be quite high. So in many cases, we need to resort to approximations and so on. All right, let's go back to the history, or let's start with the history. So Thomas Bayes, he was born in 1701-ish. It wasn't quite clear exactly when he was born. He had 6 siblings, and the family was quite wealthy. They made their money on steel cutlery. They lived in London. At this time, well, you probably know the history about all sorts of battles with the church and how in a certain period you had to use I think it was called the Book of Common Prayers or something, and sometimes you shouldn't. And well, anyway, the Church of England was very powerful, and Bayes' family was non-conformist. They didn't conform with the teachings of the Church of England. And as a non-conformist, you were banned from public office, and also you couldn't attend normal universities, and this applied to your children as well. So the common options here was to attend special non-conformist academies. Some of those were actually quite good. You could also go up to Scotland and study, or you could go to Holland. Those were the typical options that people used. So Thomas Bayes, he went to University of Edinburgh in 1719, and he trained to be a Presbyterian minister. He studied logic and some other things, and he also studied divinity and prepared to be a minister. And by the end of his study, he got his license to preach. Then he returned to London and became an assistant to his father. And after a few years of doing that, he moved to something called Turnbridge Wells, and he became a minister of his own chapel. And he stayed a minister there until 1952, when he handed over to someone else. Some sources say that he wasn't a very good preacher. I think the workload was about 1 hour of preaching, or 1-2 hours every week. And he maybe didn't enjoy that much. Right, let's look at the publication. So he started off with a publication in theology, and he was trying to answer the question of the sort of motivating the source of God's action in the world. And it was quite common at this time that you were sort of, you were very much a philosopher at the same time as you were a mathematician, for example. And as a mathematician, you had to sort of position yourself along both religious and political lines. After a few years, George Berkeley wrote a pamphlet where he attacked Newton and the way Newton treated so-called fluxions, which are differential calculus. I think he used as an example the derivation of the derivative of x to the power of n. And after a few years, Bayes came with an answer there where he defended Newton and showed why this was actually the proper way to do it. Much of the mathematics at this time was not really done with sort of rigorous formulas, but more in terms of text. All right. In 1742, he was elected to be a member or a fellow of the Royal Society. And in the nomination letter there, a certificate, it said that he was very skilled in geometry and all parts of mathematical and philosophical learning. And part of this, or through this, he sort of got access to a little informal network of peer reviews. So they were sort of exchanging works between each other and commenting that, giving each other critique and feedback so that they could improve their work, much like we do today. Here's a picture of Thomas Bayes as well, or it's not clear if it is actually him, according to some sources, but this is the picture we often see, at least. And some of this review work might have been the thing that actually made him go into the area of so-called inverse probability that we will look at closer soon. He also read a book, The Doctrine of Chances, which was very popular among gamblers. And he started working on what would become Bayes' theorem somewhere in the period of 1746 to 49. And sort of the root of this was the interest in trying to figure out the relation between cause and effect. So in the 1700s, probability wasn't really as mature as it is today, as you can imagine. It was used mainly in gambling, where it was quite handy to be able to say something about the chance of rolling three. If you roll 3 times, what's the chance of getting 6s all 3 times? It was also used in sort of philosophical questions, like trying to figure out if God exists. And also, of course, in commercial risk assessment. So if you wanted to value certain contracts, or you wanted to decide how much someone had to pay in a premium or interest rates and so on. So the problem that Bayes addressed in his work was trying to figure out the number of times an unknown event has happened and failed being given to find the chance that the probability is happening should lie somewhere between any two named degrees of probability, which sounds quite messy. Let's look at the thought experiment he used. So one of his brilliant ideas here was to design a thought experiment which would allow him to reason about this. So he imagined a table, and you would throw a ball onto this table, but you wouldn't be able to observe where it is, and it would land on the table with equal probability. So let's sort of make this a bit cleaner. So we have the table here, we throw a ball, W, then we draw a line across the table through that ball. And then we start throwing other balls, O, number of times. So we throw a ball, and then throw another one, and another one, and another one, and another one. So we've thrown a bunch of balls, and then we count the number of times it is on either side of this line here. And we consider the ones that are below to be true and the ones above to be false, for example. And then this allows us to say something about the position of that W. So we can use this physical model to find the chance of success. So getting a blue ball, and what he wanted to do was to approximate that between two numbers or values F and B. And this allows you to study the effect of the first ball, which would be the cause in this case. And then you might ask yourself, so what? Well, Bayes' theorem allows us to say something about something that can't be directly measured. In this case, it's the first ball. And this is a very powerful tool. It allows us to invert the problem, and we can use other pieces of information, which is simpler to measure maybe, to say something about that first cause. So in Bayes' thought experiment, he imagined that you threw the ball and you couldn't observe it at all. No one could see where it was, or you couldn't at least. And then he threw more balls, and you would be given information about if it was above or below. And by doing that, you could calculate, you could say something about the position of the initial ball. So why is it called inverting the probability? Well, inverting comes from, you distinguish between forward and sort of the inverse problem. In the forward problem, you have a model, you have maybe the values of parameters. In this case, it would be corresponding to knowing where the ball is on the table. And then you can generate predictions about how likely it is that if you throw more balls O that are spread uniformly over the table, what's the probability that they will become above or below that line? And in the inverse problem, you still try to find the best model to explain the data. And the data in this case would be the positions of those balls O. We talk about the inverse probability, and this is the probability of some unobserved variable. So Bayes wrote this down in a lot of pages, and then it ended with a rule that doesn't look anywhere near Bayes' rule as we see it today. And this is partly because he didn't really sort of derive Bayes' rule. He talked about trying to find those F and Bs that would specify an interval about the probability. But what it does say is that you can make observation and you can determine the most probably cause for those. And in general, we have some prior, and we get new information, and we can calculate the posterior. And especially this prior here was something that people really hated, and we will come back to that. All right, so Bayes, for some reason, decided that he wasn't going to publish this. Maybe it was modesty, maybe he wasn't sure if it's correct. So it was published after his death. I looked, if you look in Google Scholar, his essay, as it was called, has 6,973 citations, which I think if you could see that maybe think that it should deserve more citations. But it's something we take for granted for today's textbook knowledge, so you don't really cite it. All right, so the guy that decided to publish this was called Richard Price. And he published it along with a bunch of corrections, and he also added quite some material. So if I remember right, the thing he submitted was actually like 30 or 40 pages long. And he saw this as a chance to show the existence of God. All right, so why did people have such big problems with Bayes' work? First of all, priors they're qualified guesses. And if you don't agree with the prior, then you're probably not going to trust the result. In Bayes' case, he very often worked with uniform priors. So the probability of the first ball ending up somewhere was uniformly distributed, and the same with the other balls. So we use a hunch to shape the prior if you use something else than uniform, or even in uniform, we say, well, maybe we don't know more, or we suspect that it might be uniform. And if you're very rigorous and strict, then it might be hard to accept that we do something sloppy like that. And about this uniform distribution, someone said that this is really quantifying ignorance. All right, so the next step in the history belongs to Laplace. So he was born in 749. He did a lot of different things. Somewhere along the line, he found the same book that Bayes had found. He didn't really know about Bayes' work yet. And he was hoping to use this probability framework to say something about the solar system that he was trying to model. And he derived an equation that was expressed in words, where he said that the probability of a cause given some event is proportional to the probability of the event given its course, which is essentially Bayes' rule, but with the priors not there, but just sort of lumped together in some proportionality factor K. And he published this in 1974 in his memoirs on the probability of the causes given events. And chances had it that Laplace met Price in Paris in 1781. And then he was made aware of Bayes' work and this very, very clever idea of using priors. And then he worked on that for a bunch of years until 1814 to be exact. And then he arrived at the form that we know Bayes' rule today. And of course, he did a lot of other things along the way. And he died in 1827, one of the greatest scientists in the history of the world. Okay. One of the things that Laplace had done a lot during his time was to work with social scientists. He was counting populations and doing things, and statistics really took off after Laplace. But probability got a really bad reputation. And some argue that part of this is because people wrote some really bad stuff about Laplace as a person. And you really wanted to get away from this subjectiveness that was associated with priors, and you wanted to be objective, you wanted to collect data and then look at the frequency of events. And this is sort of the frequentist approach. And research into probability mathematics almost died. And so a publication as late as 1891, then a Scottish mathematician said that the laws of inverse probability that Bayes and Laplace had worked with should be decently buried out of sight and not embalmed in textbooks and examination papers. The discretations of great men like Laplace should be quietly allowed to be forgotten. So they really hated this stuff. But Bayes' work wasn't completely forgotten. As this big book I read put it, it was used in scattered niches far from the eyes of disapproving theoreticians. So the problem solvers, the ones that wanted to solve problems and didn't care what tools they used it quite a lot. Some examples, Bell used it quite a lot in their business models and system development. They had a problem that in some cities, they employed as much as 20% of the female population to be phone operators. And that wasn't a very sustainable operation. It was used in insurances. When you have to say something about want to calculate the insurance premium, and you have very little data in specific instances, but maybe you have large amounts of data on a sort of in a more general context. So maybe you don't know about the probability of getting hurt in this specific workshop, but if you say, well, this is a workshop where they deal with metal, let's look at all of those together, and we can form a prior for that. It was also used in ammunition testing during World War I, where they realized that using these frequentist approach, where the protocol said test 10% of all the ammunition, and based on how many bad cartridges you find, discard the ammunition or not. And that was a quite expensive way of testing. So people started using Bayesian hypothesis testing instead. So let's say you have two hypotheses, H0 and H1. You measure something, that might be some ammunition tests. Now you can use Bayes' rule. You can look at the probability for the different hypotheses, and you can look at the ratio specifically. So if you look at the ratio between those probabilities, we can write an expression like this. So we have the posterior odds. We have the prior odds here. So this is what we thought from the 4. You have, this is when we use all the data, we have the posterior odds. And then in the middle here, we have the likelihoods function, which is something that often is called the Bayes factor. And you can use this in many different ways. You could look, so before you do any tests, this is what you can look at. And then if you've done all the tests and plugged in all the data, you can look at this ratio. Or you can look directly at the Bayes factor, which is something that says how much you're sort of changing your idea from H0 to H1. And when the priors here are equal, then you end up with the posterior odds being equal to the Bayes factors. Yeah, in general, these hypotheses could also involve estimating a bunch of parameters, of course. And then there would be priors on those parameters. And it's also quite often to incorporate risk here. Making an error might be very risky, so you want to factor that into your decision. All right, let's get back to the history. Yeah, just to say that once you have calculated these Bayes factors, you can look up in a table and say how much does the evidence sort of support switching from your hypothesis 0 to 1. Okay, so we said that statistics was on the rising, and some of the most influential people at the time were Pearson Sr., Carl, if I remember right, and then we had Ronald Fisher, and then we had Neyman and Pearson, where Pearson is Pearson's son. And they really developed the mathematics of uncertainty. And the core here is to look at the frequency of some event A and do that in experiments. And it was also sort of very much emphasized to be objective. And Fisher supposedly said that the theory of inverse probability must be rejected. And Fisher was king at the time, and the Bayesians had to hide. Then at the time, or shortly after that, we had 2 professors at Cambridge, 2 of the greatest statisticians, maybe of all time. They were professors at Cambridge at the same time, but none of them were actually professors of statistics or mathematics. Fisher was a professor in genetics, and Jeffrey was a professor in astronomy. And they battled for years, Jeffrey being a Bayesian guy and Fisher for the frequentist approach. And Fisher, he had done a really good job in creating these nice books where he described very clearly and in an easy to use way how you should draw samples and how, based on the outcome of those samples, you could say something about the quality, for example. So it was very easy to use the work of Fisher, but Jeffrey's not so much. Then came the Second World War, This was a time when the UK was sort of shut off from the rest of Europe and the US. They got 30 million tons of goods from the US every year that had to be shipped over boat. And the Atlantic was full of U-boats that were trying to sink the boats. So there was quite a lot of activities around code breaking. The U-boats were coordinated from land via radio, and the messages were encrypted. So there was a lot of activities in trying to break those cryptos. And at some point there, Alan Turing was recruited, and he realized that you really have to make the best use of the information that you have. And this means you cannot only be completely objective. You have to sort of, really use all the information you have. And one of the things you could use is that, well, if you know something about the type of messages that are sent, that would give you information that you could start plugging into the priors. For example, if you think of the type of information they sent, then some of that information would be numbers. So in German, ein means one, or an, and that little word actually appeared in 90% of the messages. And if you know that, you can use that, and you can exploit that. And what Turing did was he tried to figure out, given all these pieces, where should I focus my attention? What hypotheses are worth considering? After the war, Churchill decided that you have to classify everything that had to do with code breaking. And the reason for that was that they still had some, there were still, I think it was the Russians that were still using some of the encryption technology that the Bletchley Park people had cracked, so they didn't want to say anything. And that meant that the world didn't know anything about Bayes being used, and they didn't know anything about Turing. And many of you probably know that Turing's life didn't turn out so well after this. All right, so we come after the war. None of the successes of Bayesian methods were known, and the Bayesians had to go into hiding. But then came one very good success, and this was in the insurance industry. And this had actually been using Bayesian ideas from the very start, and because it worked. Arthur Bailey was an actuary, so he was a risk analyst. He had studied, and his professor had told him that Bayesian's priors were more horrid than spit, which I think is a pretty strong statement. But he really set out to show that, because his professors told him the frequentist approach is the way to go. And he knew that they were using Bayesian methods, so he set out to show that what they were doing was bad. But then he realized that actually it was a pretty good idea. It's a good idea to give more weight to large volumes of data than small samples that you have drawn to assess probability. And one of the really killer arguments here is that if you have events that you have never actually sampled, then can you really assign zero probability to that? And one of the classical examples here is this probability of a mid-air collision of airplanes, which had never happened at the time. But if it happened, it would be extremely costly. And you have to factor that in when you set the premium. And Bailey wrote a very influential paper in 1950, which was one of the first Bayesian papers that sort of made the area take off. After the Second World War, the epicenter of statistics moved from the UK to the United States, and the field exploded even more. A lot of people were hired, and around 1950, you actually started to see Bayesian work appear in journals. And this was 150 years or so after the initial theory was worked out. So let's go back to using Bayes' theorem. So let's do some inference. So in many problem settings, we want to estimate some kind of parameters. Let's call it theta, and we have some data z, which we might consist of smaller pieces, Z1, Z2 up to Cn. And we want to determine the probability of this parameter theta given the measurements. And we could use Bayes' rule for that, which would give us this expression, where, as we said before, this pz given theta is referred to as the likelihood function. So let's look at an example here. Let's look at the example of positioning. So we want to position a sensor given some measurements, and we assume that we have a map of the world. And this sensor might be a sensor sitting on an autonomous car, for example. So we can use Bayes' rule in inverted problem. So we want to calculate, given the measurement, what is our position, and we can invert that and instead look at this expression where we have to work out the likelihood function when the prior for the position and the measurements. So the prior for the position is something we can often say something about. Maybe we have a bus that is moving from A to B, and we know that it starts at a certain position because this is where it always starts. Then we have some measurements. Maybe this is a LiDAR, like on the left, lower left, or it's a camera. And we have to work out the likelihood function. So this is something that given we know that where we are, so we know the position, we assume we know given position, we have to work out the likelihood or the chance of making the measurement that we just got from our camera and knowing the map that we have. And this is typically much, much simpler to work out than it is to look at the original thing that we wanted to calculate. It allows us to look not over the entire map, but we know exactly where to look, and we can work out, given that we are at a certain position, how likely is it that we measure this specific image or LiDAR scan. And then we have P measurement. And this is quite often tricky to calculate, but we often don't have to calculate it because all we really have to do is that we have to make sure that this posterior here is a proper probability density function. So we can just treat this this factor here as a normalization factor. So we work out the distribution given by the upper two terms here, and then we normalize. All right, let's get back to the inference. So to do the inference, we have to calculate or guess or agree on somehow a prior. And then we design the likelihood function somehow. So in both of these steps, it's some engineering going on typically. And then we calculate the prior using Bayes' rule. So in practice, these distributions are quite complicated and the calculations can be quite challenging. If we have high dimensional state spaces, then we often have to evaluate very high dimensional integrals, for example, and then we often have to resort to sampling-based methods. But you can do it. All right. Let's say a few words about priors as well. So one choice of a prior is to use a uniform prior. So we just say it's equally likely anywhere for all the parameters. Like going back to Bayes, the ball might end up anywhere. And this is actually an improper prior because if you integrate over the entire state space, well, not in the pool table case, but in general, this would sort of result in if you integrate over all the possible parameter value, you might get an infinite number. But we can still use this because all we have to make sure in the end is that we have a posterior distribution which is well behaved. Another option, very common one, is to use a Gaussian defined by the mean and the standard deviation. So the mean would say where is the peak here, and the standard deviation says something about the width. And this is something that fits a lot of the real world data. It's proper and it gives support everywhere, even if support everywhere means that it's non-zero everywhere. It drops very quickly to zero, but it's not non-zero. It's not zero, sorry. In general, it's nice to have a conjugate prior, which means you have a prior that results in a posterior in the same function family. for example, a Gaussian. So if you start with a Gaussian prior, you will end up with Gaussians all the time, which makes calculations easier. Okay, let's say something about Bayesian estimation. Another problem, so inference or estimation is sort of the same thing here, but in this setting, I'm thinking of the situation where we have data coming in all the time, and we would really like to make an estimate every time new data arrives. And this is something that was one of the good things actually of this Bayesian hypothesis testing that we used for ammunition testing. You could sort of sample, and then you could stop sampling once one of the hypotheses was much, much stronger than the other one. Right, so what do? Oops, we assign a prior. We calculate the posterior for that data like we showed before. And then we treat the posterior that we got as the prior in the next iteration. And then we repeat that second step for every new set of data. So let's look at this in a bit more detail. Let's say that X denotes the state that we want to estimate. This is what we call theta before, just to be a bit confusing. That might be the position of a car. Then we have some control signal U. That might be our steering wheel angle. And then we have our measurement Z. And ZK means the measurement at time K specifically. And Z1:K means all measurement from time 1 to K. The recursion Bayesian filter consists of 2 steps. One is the prediction step. This is where we sort of update the estimate we had in the previous time step. So using all the data up to time step K-1, we have estimated the state, and then we want to sort of transition that into what it might be in the next time step. We make a prediction, not incorporating new data, but just predicting how it would change. And this is something where we use the transition function. And this would typically make the distribution spread out. And then we have the update step where we incorporate new information. So we add to the measurement we had, we add the kth data point. If we look at more specifically, look at the update step in a recursion Bayesian filter, the first step, if we want to derive the equations, would be that we realize that we can split the data here into 2 parts. We can look at the last bit plus all the old ones. Then we can apply Bayes' rule, which in this case looks slightly different because we have conditioned all of the terms here on another event C, which in this case is the old data. If we use this rule here and plug in our variable or our distributions, we get this expression. And if we look at the pieces here, we see that we have our likelihood function. So the function that tells us, given that we are in a certain state X, what is the likelihood of making a certain measurement Z? We have our current prior, which is the one that we made a prediction for. And then we have the normalization constant, which we can calculate using this integral down here. So this is another example of the use of Bayes' rule in the recursive Bayesian filter. And you have 2 very common implementations of this. One is the Kalman filter, where all the distributions are models of Gaussians, and the other one is a particle filter, where we sample the distribution. And I could say a lot more because Bayes' theorem is used in many, many different places, but time is up. So to summarize, Bayes' rule was conceived at a time when probability wasn't so well defined. So you could see in some of the documents from the time. And maybe it should really be called Bayes, Price, Laplace, because each of these 3 people made significant contributions. Bayes sort of popped the initial idea. Price cleaned up the equations and corrected some things, and Laplace put it into a form that we use today. And it allows us to say something about a course for some effects that we can observe. And we also seen that this prior especially is very controversial, and many people see it as very subjective. And this is something that engineers and problem solvers, like I see myself, don't really have a big problem with that. But if you're very rigorous, then I can see that it's not so maybe nice. And it really took 150 years to get acceptance. So I don't know if that says that you should, if you have a good idea, you have to be persistent. And it's very much used today and accepted by most people. And that was the end. Thank you.